He has worked on multiple relevant projects on LLMs, including open source large language models like BloomZ, MT0, Bloom, or even large code models like SantaCoder and StarCoder. He has also collaborated on very interesting analysis papers like Bloom +1 or what language model to train if you have 1 million GPU hours. And more recently, this one, scaling data constrained language models, which is going to present today. I'm super excited to have you here, Nicholas, and thank you again for accepting the invitation. The floor is yours.
All right, thanks for having me. So in this talk, we'll cover scaling data constrained language models. The paper is up on arXiv, and this was a collaboration with lots of amazing people. I will start by looking at scaling language models more generally, a quick background on what is scaling, why are we scaling them, and how do we scale them. And then in the second part, we'll go into data constrained scaling, specifically how do we scale by repeating data, and can we mix modalities to further scale natural language and code. And then also revising existing filtering strategies to free up more data to keep on scaling. And yeah, feel free to jump in with any questions or thoughts throughout the talk. All right, so what is scaling? It really comes down to two ingredients. One is model size as measured in number of parameters. And the second one is training data as measured in number of tokens. And together, they constitute the training compute as measured in floating point operations. And they relate to each other multiplicatively. So we just multiply parameters by tokens and some constant alpha, and then we get the training compute. And over the past few years, we've kept scaling up models. So in 2018, we had BERT with 100 million parameters trained on 250 billion tokens. And together that constitutes the written flop budget of 1.6 E20. And then 2 years later, we had GPT-3, which was roughly 2,000 times the scale of BERT in terms of compute. So they scaled up both parameters and training data. And then another 2 years later, POEM was again scaled even further, about 10x the compute of GPT-3. And again, both model parameters and training data increased substantially. So why did we keep scaling language models over the past few years? The reason is that as we scale these models across these axes, we keep getting predictable performance improvements in test loss. So the lower the test loss, the better the performance here on the y-axis. And as we increase model size, training data, or compute on the x-axis for multiple orders of magnitude, we keep getting a better and better performance. And the relationship here is a power law. So as we increase across these axes, the test loss improves in a power law relationship. So given that we have these two ingredients, how should we allocate our compute to them in order to scale most efficiently? And the current consensus is you should scale equally. So you'd like to scale up model parameters on the y-axis and training data on the x-axis equally. And both axes here are in log. And the gray line corresponds to this equal scaling. And by lying directly on the gray line, the blue star, chinchilla, performs the best among all of the models depicted. So the models above, even though some of them used more compute, they are suboptimal. They perform worse than chinchilla because they over-allocated to parameters. So it's critical to scale equally. And in that same work, they also put forth a formula for directly estimating the loss L given those two ingredients, model size and training data. So we can directly estimate the performance. And they relate to each other with a bunch of constants. So we have like 5 constants, A, B, alpha, beta, and E, and then the parameters and the training data. And they fit these constants on many training runs and find that alpha is roughly equal to beta. And this corresponds to equal scaling. So if you increase n in that equation, then of course L goes down, so you get better loss and better performance. But then eventually, since alpha and beta are the same, you want to next also increase D in order to get that, to get the most additional decrease in loss, rather than just keep on scaling up N. So yeah, increase them both equally. And while number of parameters really just comes down to modifying your code, you just change the hidden size or something, and then you have more parameters, and you might have to change your hardware a bit. But overall, it's just about changing your code. Data has to be acquired externally, and it is constrained. So this plot from prior work estimates that we're running out of high quality data in the next 2 years. So on the y-axis, we have sort of the data stock in words, and on the x-axis are the years, and they estimate that given this current trend of scaling up those models, we're going to run out of data in 2024, 2025. And when we talk about high quality language data, we usually refer to stuff like papers, where there's roughly 1 trillion tokens. So that's archive, bioarchive, and so on. And then there's another 1.6 trillion tokens of books. And together, this is 2.6 trillion tokens, which is not a lot. If we go back real quick, then 2.6 trillion tokens is roughly where the chinchilla blue star is. So we're kind of already data constrained there if we're just training on these super high quality data sources. But we want to go even bigger in the future. So yeah, we have to look for that data. There's a bunch of other high quality sources like Wikipedia and so on, but it's pretty limited. We also have a lot of code. On GitHub, there's roughly 14 trillion tokens. So that might be another source of data. And then for low resource languages, we are already pretty data constrained. So recently I was working on a project building a large language model for Finnish. And that's not a super low resource language. It is pretty low resource with 6 million speakers, but there's many more languages with much less speakers. And all we were able to get was 38 billion tokens, even though we had partnerships with a few private companies and access to libraries through public partnerships. So we were pretty data constrained in that scenario. Right. So in the second half, or second part, I'll go into how we can solve those data constraints. Feel free to jump in at this point if there are any questions on the background.
Yeah, Nicholas, I'm not sure whether I should ask this now or later, but maybe just tease. So on the chinchilla laws, like you've also been involved on some projects, right? Like the Santa Coder, I believe, or the Star Coder, in which you really went way beyond the chinchilla optimal, especially in terms of tokens.
Yeah.
If you have extra compute, is that what you recommend doing? As in, if you can't go beyond the chinchilla laws, are you better off just scaling the number of tokens while keeping the parameter size, like the model size, or should you increase your scale up your model while at the sacrifice of the tokens?
Yeah, that's a great point. So I think this only considers training compute. So this is how you would optimally allocate if you want to allocate your training compute as efficiently as possible. However, if you consider inference compute, so the amount of compute spent on playing with the model, using it to predict stuff after training, then it might look very differently, because a larger model is more expensive to serve at inference time. And so actually, you'd probably want to over-allocate a bit to training data in order to have a smaller model, which is going to be cheaper to use for inference. So probably in the limit, you kind of want to allocate such that they're exactly equal. So the sort of the compute that you, or you just want to incorporate the compute you expect to spend on inference into your consideration when making this model size and training data allocation. And so for Santa Coda and a bunch of other models, we over allocated to data because of that reason, and at the cost of training a suboptimal model. So we kind of wasted some compute, or some compute wasn't as efficiently allocated as it could have been. but therefore we got a slightly better model, a model that's cheaper to use at inference.
Mm-hmm.
Did that make sense?
Yeah, I mean, when you mean suboptimal is in terms of what you could get in terms of the relationship between the number of parameters and the number of training tokens. Does that? Yeah. So my question is, my follow-up question is like, so would you think that a chinchilla optimal model, if you scale it up, would necessarily be better than a model that is smaller but trained on way more tokens?
Yeah.
Yeah. Okay.
The chinchilla optimal one will always perform better. So that's the best performance you can get. It's just that it's going to be more expensive to serve. And so you might want to spend more training compute to kind of amortize the cost at inference.
Okay, sounds good. Thanks.
And yeah, you can actually plot sort of exactly how this trade-off behaves. Like at the beginning, if you just over allocate a bit to training data, it doesn't make a huge difference. So you can safely do that. But eventually, it does make a very, very big difference. So you don't want to go too far off in that direction.
Mm-hmm.
All right, let's go into the second part. So the first idea is you can simply repeat data, right, in order to get more data. However, the current consensus, or the consensus prior to this work for training large language models, was that repetition is harmful. So in the GPT-3 work from 2020, they write data sampled without replacement during training. And then 2 years later in Palm, they say we train all three models on exactly one epoch of the data and choose the mixing proportions to avoid repeating data in any subcomponent. However, there's no clear, it's not evident why these decisions were made, why we're not repeating. So the first question we ask is repeating data really that bad? And can we quantify how bad it is? And in order to answer this question, we have three different setups. So three different core configurations that are quite large, because we have to go to those larger scales because that's the only region where it matters, right? If we train smaller models or in other areas of machine learning more generally, it's very common to repeat data. However, in order to answer this question, we're looking specifically at large language models. So we have three core configurations. The first one with 2.8 billion parameters and 55 billion training tokens, and then up to 8.7 billion parameters and 178 billion training tokens. And the way we chose those configurations is simply by taking the three compute budgets on the left and then plugging them into Chinchilla and getting the optimal allocation given the compute budget. So we just wanted to have the best model we could get given the budget. And for each of those setups, we train 8 models with different amounts of unique data that is repeated. So for the first one, with 2.8 billion parameters and 55 billion tokens, we have one model where the entire 55 billion tokens are unique, and then another model where half of that is unique and it's repeated twice. So 28 billion tokens are unique and we repeat them twice, and then a third is unique, repeated 3 times, and so on. And in addition to these runs, we have roughly 300 miscellaneous runs with different training data and different configurations. And across all runs, we use very common presets for large language models. The architecture is from GPT-2/GPT-3, so they have roughly the same architecture. And the hyperparameters are from Chinchilla. And for data sets, we use very common web crawls like C4 and Oscar. So we try not to have any confounders in the sort of the preset that we use. All right, so let's look at the value that we get out of repeating, the return. So here we have those 3 configurations. And on the y-axis, we're measuring the validation loss, which is our performance proxy. The lower, the better. And on the x-axis, we have the training tokens sort of as the model trains. So sort of the training data throughout training. And this is the first model. where across all three configurations, we're just training for one epoch. So this is sort of the baseline, the way it's commonly done. Nothing special here. For the largest one, the 8.7 billion one, of course, the loss finishes the lowest because it has the most compute allocated to it. And yeah, nothing too surprising. But then when we add the second model, surprisingly, it looks roughly the same. So this model has only half of the available unique data. So for the first configuration, it's 28 billion tokens repeated twice. However, it does seem like it performs roughly the same, just as well. So this is quite significant because it means that we can just train existing large language models on the same data that previously wasn't repeated and just repeat it for another epoch. And we just keep getting just as good performance gains as if we would have had unique data from the start. And then 3 epochs. So here only a third of the tokens are unique and they're repeated 3 times. 4, 5, 7, 14. And now we do start to see a difference. So there are diminishing returns to repeating. And then eventually at 44 epochs, it even completely diverges. So this is quite extreme. In the 44 epoch case, for the first configuration, we have 1.3 billion unique tokens and they're repeated 44 times. So it's intuitive that shouldn't work that well. And it even completely diverges. However, for few repetitions, we get roughly the same performance. And yeah, and this means that we might not have to collect as much unique data and can rather do a few more epochs on our existing unique data. And now we'll try to precisely predict how much value we're losing when we repeat data. And we hypothesized that we can measure the value of each at each repeat as exponential decay. And intuitively, that means that each time the unique data is repeated, it loses some fraction delta of its original value. And this is similar to radioactive decay in nature, and exponential decay appears in many other areas. But in radioactive decay, for example, you start with like 10 grams and then it halves to 5 grams, then to 2.5 and so on. So you always lose a fraction delta of the prior value. And then all we have to do is sum up the value at each repetition. So here we have d prime, which corresponds to the total value of our data, u, which is the unique data, and then rd, which is the number of times we repeat that unique data. And so at the first point in time, the first time we see the data, it has its full value, it's just u. And then at the second point in time, it has lost some fraction delta of its value. So it retains 1 minus delta. And then at the third time, it loses again a fraction delta of its value. So it retains 1 minus delta squared, and it becomes smaller and smaller until we reach the number of repetitions. And here, if delta is 1, then this is as if the entire value immediately decays to 0 after the first repetition. So all the other u's just become 0 and just the first one remains. Inversely, if it's 0, then it is as if repeated data is just as good as new data, because it's just u plus u plus u plus u. However, both of those scenarios are quite unlikely, given the plots we saw earlier. It's probably somewhere in between. For example, if it would be 0.5, then it would retain 50% of its value at each repetition. All right. And then we further approximate this equation to make it a bit simpler to use. So we get rid of the delta and add in this new parameter rd star, which corresponds to the number of times that you can repeat the unique data before seeing sharply diminishing returns. So if rd star is 0, then you immediately have sharply diminishing returns, and the second half just becomes 0. You're just left with u. If rd star is infinity, then you never hit sharply diminishing returns, and repeated data is just as good as new data. All right, and now we come back to chinchilla, and we plug in the equation that we just saw to replace the D in chinchilla. So this is our estimate of the value of D in the repeated scenario. And we do the same for N. So we also replace N with a symmetric version of this equation, just for parameters. And UN here, sort of the unique number of parameters, corresponds to either the optimal number of parameters given UD, so kind of the parameters that provide the optimal fit for the unique data, and we can just calculate those using chinchilla, or the actual number of parameters if they're smaller. So UD and UN sort of are this pair of optimal allocation. So if UD, for example, is if UD is 55 billion tokens, like in the setup we had earlier, then the corresponding optimal number of parameters is 2.8 billion parameters. So that would be NOPT. And so then that would be UN if our N is bigger. And then the RN value, sort of the parameter repetitions, corresponds to the ratio of N and NOPT. So if it's how often do we repeat those optimal parameters in our setup. And we call these the access parameters. Similar to how we have kind of access data in the form of repetitions, we have access parameters in the form of parameters that are beyond optimal. And they decay with the same exponential decay as the unique data. And since this formula is just an extension of chinchilla, it behaves the same way if we set RD star to infinity, so we say that repeated data does not decay in value, and we also set Rn star to infinity and say access parameters do not decay in value, then it becomes exactly the same as chinchilla. Yeah, go ahead. Okay. So it's just an extension of chinchilla that works the same way as chinchilla for non-repeated data, but then we have the kind of the option to make it work for the repeated regime and decay the value of repeated data.
Nicholas, may I ask you one thing? Sorry.
Sure.
So for clarification, I do understand the rationale on the duplication of data and on the basically on the D, the new sort of value of data. Can you sort of try to repeat again the value of the parameters and what you mean exactly by decaying in what comes to the parameters instead of the data?
Yeah, sure. So the intuition, I think, is that if you have parameters that learn from repeated data, they will end up learning the same features as previous parameters. And so you also want to decay those parameters in value. Otherwise, if we would not decay the parameters in value, then we could just, the data would decay in value, but we could just infinitely scale up a model size to get better and better performance. However, those, we can't do that, and those extra parameters decay in value. And then
I see.
Sorry, yeah, go ahead.
Yeah, so the decay in value of the parameters is associated with the decay in value of the data, right? Because if you're repeating data, then if you just scaled up your model, it wouldn't get necessarily better because you're still repeating the same data that a chinchilla optimal would be able to fit, let's say. But if you scale it up and you repeat that data, then some parameters will not learn anything beyond what could have already been learned by a smaller model.
Yeah.
Yeah. Okay.
Yeah, I think so. It comes back to this NOPT number of parameters. So you have, like, given chinchilla, you have some number of parameters that are optimal for the unique data. If you go beyond those, so if you have more than optimal, then you have to decay them in value because they're going to learn the same features sort of as those optimal parameters. If you're just at NOPT, then whatever that NOPT might be anywhere, but if you're just at that NOPT, then we assume that they learn just the right features. But if you go beyond, then they will end up learning the same features. It's just like repeating data, and they will not be as valuable as previous parameters.
Can I ask a question? I'm also trying to understand the intuition for this parameter decay. So the thing I don't really get is why, when you repeat data, you are learning the same features, because there's also an optimization issue here, right? So as you do more epochs in the same data, you are going to, you might learn better features because you make better use of the existing data. And this also goes back to the plot that you had a few slides ago. So where you showed that things diverge, the loss gets worse if you have too many repetitions, 44. This might also be because you're not tuning the upper parameters. So I mean, I would expect not to do as well as if you have less repetition, but I would not expect the curve to go up, right? So for these curves, are you using all the same hyperparameters that we use for one epoch, or are you doing tuning for specific tuning for the number of epochs and the number of repetition?
They have the same hyperparameters.
Okay, so I guess the reason why the curve goes up is that the model with 44 epochs is not correctly, the hyperparameters are not optimal, right? So it should not go up. It will probably plateau or something like that, but it should not go up.
Yes, I mean, you could of course early stop. You could add some other form of regularization, and then it might not go up indeed. So it could just be that the regularization is suboptimal. But yeah, as said, here we don't change the hyperparameters. We just leave everything the same. And so that might be the reason. Yeah.
Sorry, I was muted. So this is where I see the different, like the point you made about the decay on that explains the data repetition. This is something that is backed up empirically, right? So you have these plots and you show that you can just as well have like 4 epochs on 1/4 of the data, and you get to the same loss that you have with the entire data. That is something that I can understand. But for the repetition in the number of parameters, there is nothing empirical there, right? This is more like a argument that tries to connect. If you are repeating data, then maybe we should think about what that corresponds to in the parameters. But that is the part that I didn't completely get.
Yeah, good point. So we have empirical data on that in a few slides. However, at this point, it doesn't really matter if there's empirical data or not, because the equation, since Rn star and Rd star are just learned from the data, we just fit our data in order to learn these parameters. If the data tells us that this is not correct and parameters do not decay in value, then Rn star is just learned as infinity, and then there's no decay in value. If Rn star is infinity, then there's no decay in value in this equation. So sort of we let the data decide whether or not parameters should decay. However, empirically, we do find that there is a decay in value of excess parameters, and we have them in a few slides in the plots as well.
Okay, I see. Thanks.
Sounds good. Yeah, thanks.
But yeah, great points. So as said, we fit those two hyperparameters, or really parameterizations, the parameters of our function, Rd star and Rn star, on roughly 200 training runs, and get these values. And they'll make a bit more sense when we look at the slides where we see the decay in value of parameters. But what those correspond to is 15.4 for Rd star means that at roughly 15.4 repetitions, or roughly 16 epochs, we start to see very stark diminishing returns in the return that we get from further repetitions. And this corresponds to a delta of 0.06. So the data loses 6% of its value at each repetition. And then for Rn star, we also find that there's decay in value, and we'll see that in a few slides. So first, again, we're focusing on Rd star for this one. And here we have the final test loss on the y-axis. So this is, again, our performance proxy, and this time at the end of training. So just the final test loss measured at the end of training. And on the x-axis, we have the fraction of training tokens that are unique. So 100% is the base setup where there's nothing special. It's entirely unique data. At 50%, half the data is unique and it's repeated twice, and then 4 times at 25%, and so on. And so if we add in the first configuration, we here have the models correspond to each individual dot. So each individual dot is one empirical model trained, and then the solid line is the fit, so the loss as predicted by our scaling law that we just went through, and the dotted line that doesn't move corresponds to the loss that we would expect if repeated data would be just as good as new data. So there's no change in loss as less and less of the data is unique. And then the diagonal dashed line corresponds to the loss that we would predict if repeated data would be worth nothing. So then it just goes up diagonally. And we saw from the plots earlier that it's somewhere in between. There's some value in repeated data, but it's not as good as new data. And so we get this solid line as predicted by a formula and the fitted parameters. And it aligns fairly well with the empirical data. And then this is how it looks like for the second configuration and the third one. And it does seem like the solid line and the dots align even better as we go to the largest configuration. So it could be that the formula is slightly better at predicting larger compute allocations. And so for this one, it was entirely empirical. So we have those empirical dots. And now let's extrapolate the formula without empirical data, just extrapolate its predictions to many more training tokens. So on the y-axis are the total training tokens now. And for the first configuration, where we have 55 billion unique tokens, if we extrapolate that, if we keep repeating those 55 billion, this is how a formula would predict the loss to behave. So the solid line corresponds to the predictions by a formula of the loss. And the dotted line are the predictions if we assume that repeated data is worth just as much as new data. So this would be the predictions for a model that's trained on entirely unique data. So of course they overlap up until one epoch, but even further, they seem to overlap because as we saw, there's quite a lot of value in the first few repetitions. We are not losing that much value, but then eventually the solid line flattens out because we don't get any more value out of further repetitions. And then for 4.2 billion parameters and 8.7. And again, at 4 epochs, the repeated data is almost as good as the new data, as seen by the lines being very close. However, eventually they diverge quite a bit, and especially around the RD star value that we fitted of 15.4, they really start to diverge and eventually flatten out. So at that point, there's not a lot of value to be gained from further repetitions. Cool, and now we'll look at allocation. So
Nicholas, sorry,
yeah,
1 second. Pierre, do you have a question? Is with your
Yes.
hand raised? Yeah, okay.
So I was wondering, so how does this fit generally with the double descent story? So is the double descent another regime where like basically the model didn't have large capacity enough and you are just like far right on the curve? Or is it something that was due to misoptimization and now we know how to optimize the transformer much better? So what are your thoughts on that?
Yeah, so we have a section on double descent in the appendix, and we do see double descent happening. So it's not as if we've solved the optimization problem. We see double descent, and it does add some noise to our fit. Like when we fit all of those training runs, those 200 training runs, some of them have double descent in them, which which adds noise to the fit, because then it seems like at some point the value of a repetition goes up again and then it decreases. However, ultimately we can just fit over that noise. It doesn't add too much. And for those bigger runs, we're not seeing it a lot. So we only saw it for very small runs with like a few 100 million parameters. We didn't see it for these really big ones.
few hundred?
With a few 100 million parameters. So we have
Million?
a few, yeah, we have a few smaller runs. Actually, we'll see them in 2 slides. We'll also see the double descent phenomena there, I think, where, yeah, loss goes up throughout training and then eventually it goes down again. Kind of this.
And it's really linked to the model capacity, or there is some side story with the number of tokens as well?
I think so. It's linked to the number of tokens for sure. So it always occurs kind of at the same point in training. Maybe let me quickly.
Okay. No, but if it's next part of your story, I mean, I can.
Yeah, I can pull up the paper real quick.
Thank you.
But yeah, all right. Yeah, so it's it happens throughout training, and we've only seen it for very small models. We haven't seen it for the very large ones. And yeah, let's see. We have another slide on that. Let's see if it answers the question a bit better.
Andre, do you have a question?
Yeah, I mean, I don't know if this is going to appear later on in the presentation, but actually, 2 quick questions. One is 8.7 billion the largest models that you tried? And the second is, so this is all for perplexity, right? So do you think that the same trends also happen if you use a downstream loss, a different downstream loss?
First question, yes, 8.7 billion is the largest. And the second question, we do have performance on downstream tasks in a few slides. Yeah, and we see the same thing happening essentially.
Okay. Thank you, Nicholas. Let's go.
Thanks for the great questions. So yeah, quick reminder, for Chinchilla, it was equal scaling. However, Chinchilla assumed that we're not repeating data. And so now we'll look at how should we scale when we're repeating data. And to answer this, we train lots of models on 100 million tokens of unique data. And we vary the number of parameters and the number of repetitions. How often do we repeat those 100 million tokens? And this is how it empirically looks like. So each dot corresponds to one model trained, and we measure the final test loss. On the y-axis, we have the number of parameters of each of those models. And on the x-axis, the epochs over the 100 million tokens. And then the color of each dot corresponds to the final test loss. And we also draw contours to show how the loss landscape behaves. And in the bottom left corner, we have the kind of the baseline compute optimal model where we don't repeat any data. So we train for 100 million tokens, and the corresponding compute optimal number of parameters is 7 million. And for that model, we get a loss of 8.1. However, we can get much better loss by going into that kind of repeated data and excessive parameters regime, eventually reaching a loss of 3.7 at 59 epochs and 146 million parameters. And this is, interestingly, this is the best loss we get. And then as you go further, as you go beyond that, loss starts to increase again. So again, this could be, this might be due to the fact that we're not adding any regularization for those models. So you could just early stop and you might not see that. However, in this case, since we're just providing all models with the same hyperparameters, we're not doing any early stopping, loss goes up again, and the contours become full circles.
So here, I find this plot a little bit surprising. I would expect that with careful hyperparameter tuning, the loss keeps improving as you go up, right? As the number of parameters grows, not necessarily increasing the number of epochs because you're probably saturating. But trusting the double descent curve that Pierre was asking, what do you think about this?
I think you would definitely get it to not go up if you have perfect regularization. However, I don't think you can get it to infinitely improve as you increase parameters, because imagine the extreme scenario of having just one token. If you have 10 million parameters and you go from 10 million parameters to 100 million, you can't possibly learn anything out of that one single token that the 10 million parameters haven't already learned. Like at some point, there's just nothing you can get out of the data anymore, no matter how many parameters you're adding.
But I would expect to see some plateau, right? But what's happening here is not really a plateau, right? It seems that you are starting to decrease very quickly. You start to increase your loss very quickly, right?
Yeah. So I think a plateau would be reasonable if you have perfect hyperparameters. However, if you don't, then we see the loss going up again, similar to the diverging that we saw earlier. And yeah, this could be a result of not doing any early stopping. So if you do perfect early stopping, you have perfect regularization hyperparameters, then it might not be circles, but just curves, and it would just plateau. And I think we can also answer, or we also see some of the double descent that we talked about earlier here. So if you look at the 3.81 line, you see that as we go from dots from the left to the right, initially sort of it goes up. So here the loss is, we're in this inner circle, and then we move back, to one outer circle. So kind of the loss worsens, it goes up, but then we move back to the inner circle. So there's kind of the double descent phenomena, right? Where you first have, so loss improves, then goes up again, and then it improves again. And we have some more plots on this in the appendix, but yeah, in short, we also see double descent, and it adds some noise to the fitting. But yeah. All right. And now we'll look at how our formula would predict those same contours. So if we plug in those configurations into the formula that we put forth earlier, then we get these curves. And here, the curves are not circles, because in the formula, we only allow the value of extra data repetitions to decay to 0 and not into negative territory. So I think that kind of comes back to the question, if we have perfect hyperparameters and perfect regularization, we would expect the adding parameters and adding epochs to only plateau but never to worsen in performance. So that's the assumption that we build into the formula, and that's why we have curves instead of circles. And another reason why we have another formula in the appendix where we put forth a way how you could actually penalize extra parameters and extra epochs. However, it's not super useful to do that, because usually you never want to go into that regime anyways. You don't really want to train these kinds of super extreme models, because at that point, even at the white star, you already have very sharply diminishing returns, as seen by the increase in space between the contours. So it gets harder and harder to get, to go to the next curve to get a bit better loss. You have to spend more and more compute, because there's less and less value in each repetition. So it's not super useful to predict the exact behavior in that region, and you don't really want to go there in practice. All right, and let's add in the efficient frontiers. So again, Chinchilla says that if you're not repeating data, you want to scale equally. And this corresponds to the dashed black line. So it starts at the Chinchilla compute optimal black star, more or less, and then it just goes up diagonally, scaling up parameters and data equally. However, if we compute the efficient frontier of our formula, then it slightly branches off below Chinchilla, and eventually, heads towards that white star, and then completely vanishes, because at that point, beyond that, there's no additional value you can get from repeating data. So the value has just decayed to 0, and you can't get any better performance. And this corresponds to scaling data faster than parameters as we branch off below Chinchilla. So, the x-axis being data, we want to scale data faster than parameters when we're repeating, according to this data. And if we think back to the fit that we got, this is simply because the fit resulted in RD star being bigger than RN star. So the value of additional parameters decays faster than the value of additional repeats. So we see sharply diminishing returns and adding access parameters earlier than adding more repetitions over your data. All right, and this was pretty small scale. So this was just 100 million unique tokens. And even though we trained some pretty large models, even here, like 8 billion parameters on 100 million tokens, what we really want to see is how this pans out for very large models. So given these predictions, we train 2 much larger models. So the orange star is the first model with 8.7 billion parameters and 178 billion tokens, out of which only 1/7 is unique, and that's repeated 7 times. And this orange star lies directly on the allocation that Chinchilla would suggest, as displayed by the black line. And then we train another model that lies directly on the efficient frontier predicted by our formula, the red star, and it has less parameters on the y-axis, 6.34, however, much more data, 242 billion tokens. So that's 9.7 epochs. The unique data is the same. It's just that we do more epochs over that unique data, because our fit again suggested that, in that regime, you want to scale compute allocated to data faster, extra repetitions over your data faster than access parameters. So both of those stars, they have the same number of flops, 10 to the power of 22. The only thing we change is the allocation to parameters and repetitions. And we see that the red star performs slightly better, 2.359 versus 2.376. And actually, at these scales, this is not just slightly, it's quite significant, because if you're at that regime, you don't really see your loss improving that quickly anymore. So yeah, that difference, that does make quite a difference. And so we get slightly better performance by allocating exactly according to this data constrained efficient frontier.
Nicholas, may I ask you, so on this one, 78 billion tokens, right? Can you, like, how, this is not new data, right? This has been repeated, you've mentioned. Yeah. So it's repeated for
7 epochs, 7.1.
7, okay, I see. And the 242, it's actually repeated for longer, right? It's 9 epochs, right?
Yeah.
Okay.
So the unique data is the same. It's just the repetitions are different.
I see.
So what this slide really tells you is, if you have a certain unique data budget and a certain compute budget, then, okay, how much, how should I spend it? And it turns out you want to spend slightly more on repetitions rather than access parameters.
Yeah.
So going to 9.7. All right, so that was repeating. And now we'll briefly look at 2 additional strategies for solving data constraints. The first one is filling the missing data with code. So instead of repeating your data budget, you just adding code from those trillions of tokens on GitHub that we discussed. And another strategy we'll look at is changing existing filtering strategies. So it's very common to filter those large web crawls. However, this can limit the available data a lot. So we look at if it's really worthwhile. So we train 97 models for the same number of flops. And those models have 4.2 billion parameters and are trained for 84 billion tokens. And then on the y-axis, we display the performance of each of those models across 19 natural language tasks. And on the x-axis is the data budget. So how much of their training data is available. At 100%, it's just the baseline where the full number of tokens are available. We don't have to repeat. We don't have to fill with missing data or anything else, fill the missing data with Python code or something. But then as we go to the right, and more of that data budget is not available, and we have to use those strategies to make up for the missing data. And then we have all of those dots corresponding to one model for repeating and filling the red and purple lines. We also display the standard deviation corresponding to 5 average seeds. And so starting with repeating data, the purple line, the first thing we see is that it confirms our findings from earlier, now on downstream data. So also on downstream data, we see that you don't get any performance penalty from doing a few repeats. So 25% data budget, we have to repeat the data 4 times. And despite that, the performance is roughly the same as at the beginning, even goes up slightly, but it's within the standard deviation. However, then eventually performance drops a lot, and repeating starts to not bring in as much performance gains. So this is similar to the findings on perplexity that we had earlier. And then the red line corresponding to filling the missing data with Python code, it starts off. So at the beginning, of course, it's the same, because in that case, we're not doing any filling. But even then, as we have less and less data available, the performance remains roughly the same, suggesting that, we can fill up with, say, 60% of code, and the performance is still just as good as if we would have had that much unique natural language data. And the benchmarks that we use here are all natural language tasks, like Winograd schemas, COPA, and so on. So that's quite surprising. We're not benchmarking any code tasks. And finally, deduplicating clean data sets might not always be helpful. So the orange star corresponds to taking a C4, like a slightly filtered web crawl, and deduplicating it again. So removing common substrings. And that actually hurts performance. So we might be removing too much data. So you want to be careful with excessive deduplication. All right. So now we'll go through the takeaways. First, we looked at scaling and established that scaling is super important for progress, but we're data constrained. And then the first way we investigated to solve those data constraints is repeating. And from empirical data, we saw that we can repeat safely 4, even up to 8 times. However, there are diminishing returns, and we can predict those. And we also saw that when we're in that repeated regime, we should scale compute allocated to repeated data slightly faster than number of parameters. And finally, we looked at some complementary strategies to solve those data constraints, and found that adding code gives us another 2x without penalty on natural language performance. And we should be careful with too much deduplication, which can limit the available data a lot. Thanks.
Thank you, Nicholas. This was great. It's a very nice talk, lots of findings. I think this is extremely relevant work nowadays. I do have one question. Maybe I can ask if the audience, if anyone has questions. Yes, Pierre, go ahead.
It's really open. So in all this work, and in general, when you are scaling low, you assume that you never talk about quality beyond deduplication or like beyond repeating.
Yeah.
So how does, I guess you could refit the law, but like, what would it change if you, do you see another behavior, like if you have like really good data?
So we have an experiment with the opposite, with worse data. So the experiments that we looked at were all on C4, which is a somewhat filtered web crawl. And we also ran most of those experiments on Oscar, which is another web crawl, which is a bit more noisy. And we found the the behavior with repetitions, kind of the decay in value to be pretty much the same. The difference was just that the performance was worse after training on Oscar versus C4.
But for instance, I'm speaking about quality. You know, for instance, you mix a lot of sources.
Mm-hmm.
So if you have less sources, or like more sources, like, I mean, so if you have a lot of sources with only like a few representative data, so do you have some intuition how would that change? It's super open now.
Yeah, it's a good question. It comes down to sort of, I think one dimension of that is like the mixing proportions, or like what kind of data you mix, or sort of the inherent diversity of your data, I guess, how that affects the loss. Beyond the GitHub plus natural language, we don't do any mixing experiments. So sort of GitHub plus C4, and then of course you could kind of look at C4, what kind of components are in there. But yeah, we don't have experiments on that, unfortunately. But I think it's super interesting for follow-up work.
Okay, thank you very much.
Yeah, so I think this goes in line with what Pierre was mentioning, because I mean, if you can afford to have, say now you have more data, right? You have C4, but you can afford to aggressively filter C4 because now you can repeat some of that data for a number of epochs, and it's okay. Is that worth it? That is my question. If the price of aggressively filtering out data in then sacrificing seeing new data, but probably seeing better data, but more repeated data, that's the perplexity. That's sort of that star there.
Yeah.
It seems to actually turns out to be quite good, right?
Yeah, I think that's a great point. It can be worth it. So as you mentioned, the yellow star where we use perplexity filtering, it improves performance. So we perplexity filter and then repeat. Since after filtering we have less data available, we have to repeat it, and then we repeat it and we get better performance than the others. So that's definitely a super interesting avenue. You know, should you filter first, or do some specific filtering and then repeat that, because repeating isn't as bad as previously thought. And another example of this is if you repeat so this is again trained on natural language data. Here's C4, and if you repeat C4 twice, you're still getting better performance than on the training on Oscar just once. So the other model, the other data set that we have ablations on in the appendix. So you're better off sometimes doing some additional filtering and then repeating, rather than less filtering and not repeating.
Yeah. I do wonder about another thing. So a lot of works incentivize not repeating the data or deduplicating the data. I think this first came from the stream of analyzing memorization, right? The idea being that if you do not if you duplicate your data, you are reducing the likelihood of memorization, which can possibly be bad for some use cases. Have you tested this, or have you analyzed memorization in these runs?
Yeah, it's a good point. We didn't look at memorization. It's kind of a separate dimension. Like if you think that's bad, if your model memorizes, then that's sort of another. So here we just focus on performance. Does the duplicating improve performance? But if you also care about memorization, then maybe that's another kind of axis that you might want to look at. Yeah, obviously repeating is probably also going to increase memorization. So in that sense, if you want the model not to memorize anything, then repeating might not be such a good idea. Yeah.
Mm-hmm. Okay, so I would like to go back to some of those previous points, because we've been having some discussion. So say we have now seen like the lemmas, especially, right? They're training smaller models, right? But for a huge amount of tokens, way beyond the chinchilla optimals, right? And they do these models seem to not being saturating in terms of the loss, right? It seems to still go down, right? Which at first seems to be it seems to be like, when will it stop, right? And is it just that you can really go far with these smaller models by just, or would Llama be better, or Meta be better, if instead of using a 7 billion model trained on 2 trillion tokens, if they instead went and it's scaled up these models and used less data, as in training a, say, 30 billion model, but with less tokens? The chinchilla say, well, they do hold similar value to some extent, but I would just like your thoughts on that, on that regime of going way beyond chinchilla laws in training tokens.
Yeah, I think it makes sense. So I think you can go much further and loss will keep going down. And it makes sense if you expect to use those models a lot at inference. So it really depends on how much do you expect to use the model at inference time. If you expect to use it a lot, then it's probably worth sacrificing. So in a sense, you're sacrificing training compute. That's, because you're suboptimally allocating it by training on too much data. But that sacrifice might be worth it if the sort of the gain in inference compute that you get from having a smaller model is bigger. If that makes sense. So I think you can kind of compare. So how much training compute am I sacrificing by using it suboptimally versus how much training compute am I gaining, inference compute am I gaining from having a smaller model? And you probably want to do it such that those are equal. So you want to sacrifice just as much compute by training a suboptimal model as you expect to gain at inference by having a smaller model, because it's cheaper to use a smaller model at inference. And for Llama, since they're used a lot and they have a huge impact, I think it's worth it sacrificing some of that training compute and therefore having cheaper inference.
Mm-hmm. Yeah. So in the limit, could Meta do like that's my question. If it would saturate, because say you have a 1 billion, 2 billion, 3 billion model, right? But trained for lots and lots of tokens, right? You would need way more tokens than Llama used, right? But to get to the same point. But there are some arguments for scale that go beyond just performance, like the emergence capabilities that may appear at some scale. Do you think you can all get these sort of capabilities, these sort of performance just from data alone, or you do really need the capacity to get that?
Yes, I think the those emergent capabilities, they really emerge as a function of compute. So, you might, if you're going compute suboptimal, you will need a bit more compute to get those than if you're allocating compute optimally, but you will also get them. So you can also get them at 7 billion parameters if you allocate enough compute to it, I think.
Yeah. Okay. Okay. I don't think we have more questions from the audience. Yeah, I think that's it. Nicholas, thank you once again. This has been such a great talk and nice discussion. I hope you can continue making great work so that we can invite you back in the future. And all the best to you, and enjoy your background. It seems lovely. So yeah.
Thanks a lot for having me. It was a lot of fun. Super interesting.